Okay, so let's begin with the first of the two problems for today, which is titled combination sum 4, although the title is quite uh, meaningless, as you'll see. So the problem is as follows. You're given an array called nums, and it has distinct integers, and you're given a target integer. You want to return the number of possible combinations that add up to target. And the answer is guaranteed to fit in a 32-bit integer. So the way the problem is described is again a little abstract and uh, somewhat unclear. What exactly is this problem? So instead of calling it combination sum 4, I'm actually going to call it coin change in preparation for the next problem as well, which is coin change 2. But on lead code, coin change is an optimization problem where you have to minimize the number of coins needed to make up a certain amount. So I don't want to use the same name. So let's call it coin change count permutations version. The next problem that we look at, I'm going to call this coin change count. The subsets version. That's how these two problems are related, and you'll understand what exactly these two versions mean as we are going through them. So we are going to interpret these numbers that are given to us in this array nums as a set of distinct coin denominations. So let's consider these as coin denominations. That means something like 1 cent coins, 5 cent coins, 10 cent coins, 25 cent coins, and so on. So of course, with the American coin change problem, if you've looked at my, I think in one of the ad hoc floaters, I take that up as a classic example of a problem that can be solved using a greedy approach. And I think even in the foundation videos, we've gone through the fact that a general coin change problem uh, will not work correctly if you use a greedy approach. But with special values, which are multiples of each other, um, a greedy approach would work. But I'm not going to, since the American coin change problem has been discussed in a lot of detail uh, in I think the first class on greedy algorithms, I'm not going to discuss that here. We'll assume that these coins can be arbitrary values, and they're all distinct because they're coin denominations, so it makes sense for them to all be distinct. And this target integer is a certain amount that we have to make up. Okay, I need to reshare since the screen is frozen. So the target integer is an amount that we have to make up using those coin denominations. And what we need to count in this problem is the number of ways in which we can make up the given amount. The answer is guaranteed to fit in a 32-bit integer, which means we don't have to do a mod with using a large prime number like 10 to the power 9 plus 7, which you might remember we had to do in the tiling problem. So the answer, the inputs are in a range that the answer is guaranteed not to overflow. So let's look at the two toy examples they've given here. So let's say our coins are 1 cent coins, 2 cent coins, and 3 cent coins, and we are allowed to pick as many copies of these coins as possible. So assume that we have an infinite supply of each coin denomination. How do we make up 4 cents out of these three denominations? So they have listed here the different ways in which we can pick and arrange the coins so that the total is 4 cents. So 1111, 112, 121. And what you will notice from these examples here is that they are the same three coins. It's just that they have been rearranged. So, in other words, order matters. It's not. Uh, it's not just a matter of counting which how many copies of each denomination make up the amount. We also need to treat different um, arrangements of these coins as different ways of making up the amount. So 1 3 and 3 1 are also treated as distinct combinations, if you want to call it that. So that's why I think this word is misleading, because uh, the word combination typically stands for subsets, as you know, but in some contexts you can say a combinatorial object is just an object that is made up of it's a composite object that's made by combining a bunch of simpler objects together. And when order matters, that combinatorial object is a permutation. When order does not matter, that combinatorial object is a subset or a combination. So the word combination, therefore, is ambiguous in this context. Uh, but what they actually mean here is something like a combinatorial object, right? Because order matters, so that's why I have called this as the permutations version of the problem. So different sequences are counted as different combinations, or we should say different combinatorial objects. They are essentially different permutations. So there are 7 different uh, permutations, or 7 different coin combinations which sum up to a target value of 4, and so the answer is 7. In the second toy example, there's only one coin denomination you're given, which is a 9-cent coin. So how can you combine 9-cent coins together to make up a target amount of 3 cents? Obviously, there's no way to do that. So the output is supposed to be 0 in that case. So I hope this problem now makes sense. Uh, the name is misleading. Think of it as the coin change problem, permutations version. So let's take a couple of minutes to think about this. And unlike last time, what I'll do is I will first go through my thought process, since I got some feedback from some of you that it was not very helpful to listen to different people uh, putting forth multiple different ideas at the same time, and mixing them together. So I'll go through my thought process first, and then after that I will check what questions you have, and if you have other approaches or other ideas, we can take them up once we have gone through one complete um, explanation of the thought process, end to end. But having said that, if you have any questions right now about the problem statement, feel free to ask. You can just raise your hands, and I'll try to answer questions on the problem statement. Yeah, Pratik.
Yeah, Omkar, can you hear me?
Yeah.
Yeah, so uh, you say that this is a permutations version. So permutation is usually rearranging the same values in different orders, right? And here we see some of the answers are actually the subset of the given input. Uh, like 1, 3 is just a subset of the given larger input, which is of three numbers.
Yeah. So um, yes, it is a subset, but then when you order the elements of the subset in different ways, they get treated as different combinations, right? So you can either think of this as a subset uh, you can create you create permutations out of the subsets, right? And
Oh,
you count not just the subsets. So this combination sum is not literally a subset sum. It's not the number of ways of forming subsets which add up to the target. It's actually uh, an ordered subset problem, if you want to call it that, ordered subset sum problem.
okay. It just came. I just realized. So basically, here target would be a constraint on that permutation. Otherwise, if there was no target, then the permutation would exactly include that many results, right?
Yeah, so you're allowed to pick as many copies of each denomination as you want because there is a target.
Okay,
Otherwise, there is an infinite supply of each coin denomination. So without that target constraint, there'll be an infinite number of subsets or even permutations that you can form by picking one or more of these coins. So we are specifically interested in how many of them add up to the target, and uh, we treat rearrangements of the same subset written in elements written in different order as uh, different ways of constructing the target.
got it. Okay, thank you.
Okay, so I'm just going to give everyone a minute to reflect on this. Okay, so the very first natural approach that you would want to try would be, you can say, a brute force approach, where you try to do an exhaustive search across all such subsets. So exhaustively check all possible subsets, right? Just like you might exhaustively check all possible tilings for the problem we did last time. Uh, Now, even the narrow canonical definition of the subset sum problem, where you are given, you might remember this from your recursion week, or yeah, I think in the recursion week you do the subset sum problem, right? Where you're given a set of numbers, distinct numbers. You want to find out how many subsets of those numbers add up to a particular target. So there, the word subset is literally meant like a subset, as in it either includes or excludes each of the numbers that you're given. So you can enumerate every single subset and check whether each subset adds up to the target. So you can do something like that even here, which is to exhaustively try all possible subsets, try to construct all possible subsets, uh, and see how many add up to the target. Now it doesn't require you to actually think about the implementation in detail to see that this is going to take exponential time, because even if you were not allowed to pick multiple copies of the same coin, assume that this array nums that you are given of coins were individual coins. Even trying out all subsets of those individual coins, where each coin either appears 0 times or once, right? Either excluding or including it, that would need order 2 to the power n time, right? If n is the length of the array that you're given. So there are two inputs here, right? One input is n, the other input is you can say t, which is the target amount. When we check all possible subsets, uh, the number of all possible subsets is going to be at least 2 to the power n. Actually, it's going to be more for the problem that we are looking at, because you can include a particular coin multiple times. But even if we had to either include it once or exclude it, there would be two choices for each coin, and so there would be 2 to the power n different subsets. So clearly the number of subsets is greater than 2 to the power n here. And so trying each of them out is definitely going to result in a time complexity that is exponential in n, right? So that's why um, um, this is that it would be a correct solution if you were to try all possible subsets, but um, firstly it would be exponential time. And so um, another way to argue this is, suppose I mean, for the given problem, we give you an example of how for the given problem the number of subsets could be exponential if we try to enumerate each of them. So let's say we had only two coins, 1 cent and 2 cent coins, and we had an amount of let's say some number 3n by 2, okay, where n is some large number. So one way to make up an amount of 3n by 2 is to use n by 2 1 cent coins and n by 2 2 cent coins. So I'm basically coming up with an amount which is going to require n or n by 2, you can say 1 cent coins, n by 2 2 cent coins. In other words, a total of n coins, half of which are 1, half of which are 2, and they make up the target amount. I'm choosing the target amount in that way, so that my subset has n by 2 coins of one type, n by 2 coins of another type. Now, since their rearrangements also matter, right? So the number of possible rearrangements just of uh, a subset of coins where n by 2 are of one type, n by 2 are of another type, would be factorial n divided by factorial n by 2 times factorial n by 2. Right? Just like if I have a bunch of zeros and ones, let's say there are n of them in total, or let's say there are 2n of them in total, right? Just so that n, half of them is actually also an integer. So let's say there are 2n, there's a bit string of zeros and ones, which is of length 2n. N of them are 0, so there are n zeros and n ones. How many different permutations are possible of this bit string? Well, it's going to be factorial 2n divided by factorial n times factorial n, because factorial 2n is what you would have if uh, all of these values were distinct, but n of them happen to be the same, so we divide by factorial n, and the other n also happen to be the same, so we divide further by factorial of n. And this value, as you know, is just another way to write 2n choose n, right, or 2n cn. Likewise, this value is can just be written as n choose n by 2. So anyway, it doesn't matter whether we pick this as n or this as 2n and this as n. We essentially get an n choose k value, which we know in general is going to be an exponential, right? From, again, hopefully you remember the foundation videos for this. So, and we haven't even looked at other possible ways of making up the target amount. We just looked at one single subset and its rearrangements, and that's already exponential. So the question is, can we do better? And to understand how we could do better, we can note the following um, we can note, well, before I come to that, any questions about this brute force approach? I'm not elaborating on that in detail because even though it's correct, it's going to take a lot of time, and so we clearly need to do this faster. So the question is, why do we think we could do faster? Um, and the answer is that in enumerating all of these subsets, um, there are going to be overlapping subproblems, right? We might have, um, so let me explain it this way. Let's try a decrease and conquer approach. Where actually, before I do that, let me also explain the same problem to you in a different way. Instead of using coin change, let me also map the exactly the same problem to a different word problem. In fact, to two other word problems. So recall last time we did the tiling problem, right? So imagine you are given a 1 by n board, right? This is a 1 by n board of squares, and you're given a bunch of tiles. I should say 1 by t, I guess, just to be consistent, or 1 by a for the amount, or let's say t. You're given a bunch of tiles in the form of this array nums, and you can think of them as um, tiles of different dimensions. So, for example, if the nums array is, let's say, 2 comma 3, that means you have two different types of tiles. You have a 1 by 2 tile and a 1 by 3 tile. Right? If nums was this, that means we have two different types of tiles. And so this question is, in how many ways can we tile this entire 1 by t board using only tiles of these two types? Right? So this becomes exactly the problem that we did last time. The problem we did last time, in fact, is a more complicated version. This is an even easier version because there's only one row here. Right? I hope you see that it's identical to, interpreting it as a coin change problem. You're given a bunch of tiles, and uh, clearly order matters because if t was 5, one way to make up uh, to tile a 1 by 5 board would be to have this tile followed by this tile. Another way would be to have the 1 by 3 tile first on the left, and then the 1 by 2 tile to its right. So these are two different tilings of the same uh, board. And so we want to count how many different tilings there are under this description. So it's the same thing that the same abstract problem, just stated in a different way. Yet another way to uh, describe this problem is to map it to the climbing stairs problem. Suppose you had a bunch of stairs, and the total number of steps you need to take to go from the bottom to the top is, let's say, t. And in each step, or in each direct jump, you can either climb up 2 steps at a time or 3 steps at a time. The climbing stairs problem that we did in the foundation videos um, allowed you to take only one step at a time or two steps at a time. But we can generalize it and say maybe this array nums will tell us what are the distinct jump sizes that we're allowed to take, and we can mix and match them, and we can jump as many times as we want with each jump size, as long as we can go from the bottom to the top. So a jump of 2 followed by a jump of 3 is different from a jump of 3 followed by a jump of 2, even though the result might be the same. Right? So you could interpret this same problem using a climbing stairs lens as well. Given an array of distinct direct jump sizes and a target number of steps that have to be climbed, return the number of unique paths that uh, take you from the bottom to the top, that take that those many steps. So clearly order matters in all of these problems. And just like the same analysis that we had done in the foundation videos for climbing stairs, uh, the number of different ways of climbing up a sequence of stairs will in general be an exponential. And so we want to do better than exponential time. So let's try a decrease and conquer approach and see if that leads us to an improved runtime. So a decrease and conquer approach would ask, well, in the climbing stairs problem, we asked, well, what's the last step? What was the last move size? Uh, was it 1 or 2 in the foundation video problem? Here we would ask, is it 2 or 3? Or if we thought of this as a tiling problem, we would ask, like we did last time, what's the last tile like? Right? The tile that covers the rightmost square of the board. Uh, what tile is that? What are the options for that? I'm just going to focus like a lazy manager on the rightmost cell and ask what are the options for that. Similarly, for this coin change count context, as a lazy manager, I could ask um, what is the last cent um, going to be covered by? Instead of the last square in the tiling problem, what's the last cent going to be covered by? Another way to ask the same thing is, what's the last coin? What's the final or the last coin which makes up the target amount, right? If you were to imagine laying down all these coins in a linear order from left to right, what's the rightmost coin? We know all of them need to add up to the target, and so we ask that question. So if nums was something like, let's say nums was 2 comma 3, clearly the last coin could be either a 2 or it could be a 3. If this was a much longer list, then we would have many more options. So as a lazy manager, I take the responsibility only for looking at what the last coin should be. So let's say the last coin was a 2-cent coin, or it could be a 3-cent coin. So if it was a 2-cent coin, I want to know from my subordinate how many ways are there to make up a target amount of not t. So for me, the target value might be, let's say, t, But I am saying if the last coin was a 2 cent coin, then I want to know from one of my subordinates what are the number of ways of making up a target amount of t minus 2, right? That's the remaining subproblem. Likewise, I want to know from another of my hires what are the number of ways of making up a target amount of t minus 3, because I'm assuming 3 cents as the last coin. So if my left subordinate comes back and tells me that there are 25 ways of making up a target amount of t minus 2, then I can conclude that there are 25 ways of making up a target amount of t where the last coin is a 2 cent coin. Same thing for my right subordinate. Whatever count my right subordinate comes back with, that's also the count of the number of ways of making up a target amount of t where 3 cents is the last coin. So the total number of ways of making up a target amount of t would be the sum of the answers returned by my two subordinates. Now, because my subordinates are lazy, they're going to be doing the same thing. So they will ask what's the last coin that can make up a target amount of t minus 2. And so there could be a 2 cent option and a 3 cent option. Likewise, here there could be a 2 cent option and a 3 cent option. So if you look at these second level subordinates, the target amount uh, here is t minus 2 minus 3. So it's t minus 5. Here also the target amount is t minus 5. Here it's t minus 6. Here it's t minus 4. But then if we keep expanding, if we look at the next level choice, we're going to get to t minus 6. So you can see there are subproblems that are looking identical at many places in this tree that we are as we expand out each level. So these are overlapping subproblems, these two are overlapping subproblems, and there'll be many more you'll find. Okay, so overlapping subproblems. Because there are overlapping subproblems, there is scope for using dynamic programming. So what we started out with, a straightforward decrease and conquer approach, is now heading in the direction of dynamic programming. Hopefully with that, we might be able to cut down the complexity uh, from exponential to something polynomial. If we didn't use dynamic programming, you can see that this tree that is built out will be exponential in size for the same reason that if this was 1 and 2, this would essentially be the Fibonacci sequence tree. Right? So it's clearly exponential in size, as you might remember from the foundations. So it doesn't matter whether it's 1 comma 2 or 2 comma 3 or whatever, it's going to be some exponential. So plain decrease and conquer implemented recursively would also not improve uh, on what we started out with, which was the brute force approach. But with dynamic programming, we would hopefully get something better. So how do we do dynamic programming here? Well, we first have to take this corporate hierarchy and eliminate redundancy by merging together nodes that correspond to the same subproblem, so that each subproblem appears only once in this tree, which will convert this tree into some kind of DAG, right? Assuming that we have arrows on the edges from each worker to his or her manager, we will get a dependency DAG. And so the question is, how many distinct subproblems will we have when we eliminate that redundancy in the dependency DAG? So if we ask that question, uh, we know that the subproblem definition for each worker is given a particular target amount, figure out how many ways there are to make up that target amount using exactly the same array, the original nums array. Everyone has access to that same nums array. So what really differs from each subproblem to another is the target amount. Now the target value uh, was, let's say, some constant t that was given to you in the problem. So the number of distinct subproblems in the dependency DAG will thus be the number of different values that that target amount can take for each manager. So that's just going to be, t minus 1, t minus 2, all the way down to, let's say, 0. So that's t plus 1. There are t plus 1 distinct subproblems in the dependency DAG. And each subproblem depends on two other subproblems that have smaller values of t. So if we were to uh, look at the subproblem where the target is t, it's going to depend on the subproblem where the targets are t minus 2 and t minus 3. Maybe we don't need t minus 1, but it's going to look like this. And then for t minus 1 also, we'll have two arrows coming from below. For t minus 2 also, we'll have two arrows coming from below. And so it makes sense then to compute the solutions to all these subproblems in topological sort order from uh, an amount, a base case amount of 0, all the way up to the given amount t. So the solution to each subproblem will be stored in a cell, and since this topological sort is looking like a linear list here, we will just store the results of all these, the solutions to all these subproblems in a linear structure like an array. So let's say the solution to this subproblem is going to be stored here, solution to this subproblem will be stored here, and so on. So we allocate a table of size t plus 1 and we start filling in the table from left to right. So the leftmost value, let's say it's 0, needs to be filled in by us explicitly. So how many ways are there to construct an amount of 0 cents given whatever set of denominations we are given? But there's only one way, which is the empty subset. We exclude every coin. Um, so essentially we have an empty permutation uh, which would create that amount. So we know that um, table of 0 will be 1. For subsequent amounts, we can rely on this kind of a structure to say we are going to look below us or look to our left for solutions to two smaller subproblems. Now in theory, how many places do we need to look back? That is going to be given by what the specific coin denominations are. If we have a coin with a denomination of 25 cents, we'll need to look 25 places to our left to see what the value stored there is, and then take that value and add it to the values that are stored in other cells that we look back based on the other coin denomination values. So if our biggest coin denomination is, let's say, 25 cents, we need 25 base cases to to be filled in. Now we could work with the 25 base cases starting from index 0, or we might even say that there is no way to construct a negative amount. So we can imagine base cases heading all the way here from an amount of -1 to -24, all with a value of 0. So if I am thinking of constructing a 1 cent amount, and if I subtract 25 cents from it, I get a negative value, and any negative value I know cannot be made up. So it's like, look, it's like, having an infinite number of base cases all with a value of 0. So uh, that is where we are, and so we need to uh, define the subproblem, let's say in plain English. And so let's say f of t is the number of ways of constructing an amount t using the coins in the nums array. So if we were to write f of t more formally as a recurrence, we would say that uh, f of t, just like here with two values in our nums array, we would subtract those two values from our target t and look at the solutions, compute the solutions for those two smaller subproblems and add them together. So effectively, we are adding together a bunch of uh, solutions to subproblems, where each subproblem has a target value given by t minus whatever the coin denomination is, right? So since we are talking about the nums array, nums of I would be the ith coin denomination. So if we so this is going to be our ith subproblem, or the subproblem solved by our ith subordinate. So whatever the solution returned by our ith subordinate is, we're going to take that and add it to solutions returned by other subproblems, other subordinates. So I would vary from 0 to whatever length of nums minus 1. These are all the coins that we have. Okay. So this is our recurrence, and notice that if our nums was just 1 comma 2, right, if nums was just 1 comma 2, this would be nothing but f of t minus 1 plus f of t minus 2, which would be the Fibonacci recurrence, or the recurrence we got in the climbing stairs problem in the foundation videos. So this is a generalization where we have uh, multiple options at each step. So it's a longer summation. Instead of just having two terms, it will have n terms in general. So this is the recurrence that we are going to essentially mimic when we write the code for this. Right. So I'm gonna write the code, but any questions so far on the thought process or the steps that have led up to this point? You can just raise your hands in the participants window if you have questions. So we will allocate a table which is going to be a 1D array of size t plus 1. Right? Let's say it's initialized to 0. I mean, it doesn't matter what it's initialized to, we can always overwrite all the values for the recursive cases. But on the left extreme, we are going to have table of 0 being equal to 1. This is our base case. And implicitly, everything to the left with negative target amounts, they are also like base cases with a value of 0. And then we have a loop that is going to uh, traverse the subproblem DAG in topological sort order. So we'll have I varying from 1 through T, the final target amount. And we are going to compute f of I in the body of this loop and store it in table of I. How do we compute f of I? By going back to the recurrence and then just implementing it. So for each coin in our nums array, we are going to look at the previous result and add it uh, to a cumulative sum, or add it to whatever the, so initializing everything to 0 is good because our cumulative sum starts out being 0 for any I, and so every time we find a value here, we just increment the table of I value by that amount. So for each coin, uh, in the nums array, well, let me write it using more generic pseudocode. So for each, actually this might be more readable, so let me keep it like this. For each coin in the nums array, okay, instead of writing it as for C in range, in the range from 0 through length of nums minus 1, nums of C would be the denomination of the coin. But I hope you understand that when I write this, the coin variable is taking the value of uh, the next coin denomination. So for each coin in nums, we are going to subtract this coin value from T. That will give us our subproblem size, and we will look up the solution in our table, which is going to be in which is going to be in the at the index I minus coin, my I minus that coin denomination. We'll look up what that value is, and then we need to add it to the summation, right? Or in other words, all this is accumulating into the value of table of I, so we just increment table of I with the solution to that previous subproblem. Now the issue is that there will be cases where this value I minus a particular coin denomination might become negative. And so if we go back to this diagram, becoming negative means we are going back to a base case that is in the negative range. And so the contribution or the solution to those subproblems is implicitly a 0. So we are not going to increment table of I if we fall back on one of those cases. So in other words, we do this only if we are not, if as long as I is greater than or equal to coin. So as long as I minus coin, this subproblem size, is at least 0, we will do this. And once this for loop runs t times the outer loop, the final value is going to be sitting over here. So we will just return that table of t. So how much time did this take? So the time complexity of this piece of dynamic programming code is, so it's basically a double for loop with fixed boundaries. So there are n. So this inner for loop is going to run n times, where n is the length of the nums array, and the outer for loop is always going to run t times. So the time is going to be n times t. The space we have used is order t. This might be optimized depending on how big these coin denomination values are, but let's keep it like this for now. So it's order um, um, it's order t plus 1, which is the same as order t. Now this is much better than the exponential time we had before. It actually wasn't just 2 to the power n, it was potentially more than that. Uh, so dynamic programming has allowed us to cut down the complexity. There is a catch though, which is also a catch with the basic version of the subset sum problem. If my target amount is uh, is really long, let's say it's more than 2 to the power n, then this is still going to be exponential. Okay, this is also an issue with the dynamic programming based solution for the basic subset sum problem. So yes, dynamic programming is bringing down the time complexity provided our target value is not too big. If it's more than 2 to the power n, then our table is going to be of length more than 2 to the power n. So obviously filling it up is going to take time more than 2 to the power n, in which case we might be better off just uh, looking at a brute force approach where you just enumerate all subsets. Right, because there when once you enumerate all subsets, um, well, in the subset sum problem there are only 2 to the power n subsets. Here there might be more. um, yeah, here you will need to keep building up subsets to a point where the subset sum does not cross t. So yeah, it may not, the brute force approach may not work faster than this, but this approach is not going to be significantly better if we have a target value that's very big. Okay, that completes my thought process behind this problem, and now let's see if you have any comments or questions. Yeah, Amey.
Omkar, thank you very much for this session. So I'm just curious, like the decision of taking 1D array. So how did you took decision? Because usually this looks like unbounded knapsack kind of problem. So usually I start with the 2D and I try to find out like if it states if current state is depending on just like previous state, then you can go
Mm.
for the 2D array.
Yeah, so
I
you
mean
will
1D array.
see, yeah, you will see that in the next problem, because in the next problem, uh, we might end up with a 2D array, at least to start with. So what I did is I just asked this basic decrease and conquer question, which is what I'll do in the next problem also. So uh, once we know what the subproblem DAG is like, based on that we decide what the data structure should be. If the subproblem DAG has is only of uh, size t and the subproblems are labeled from 0 to t, it's very convenient to use an array with those subproblem sizes as the indices. Last time, if you recall, or at least or maybe even the first dynamic programming series video, where I had an f function, an L function, and a U function, if you were there in the previous class. There, our subproblem DAG had 3n values, and so we would have three arrays of which are 1D. In the unique paths problem, uh, I think where you have a 2D grid, every cell in that subproblem becomes a sorry, every cell in that grid maps to its own subproblem, and so there the subproblem DAG is a regular two-dimensional. It has a regular two-dimensional visual representation, and so our table also has a two-dimensional representation. Now, but that's a separate problem. You will see in the next problem that this analysis is going to be more complicated. So we might have to start with a 2D table there. Uh, so maybe your question will be fully answered once we go through the second problem, because we can compare and contrast that with this. Is that good enough for
It-
now?
yeah, yeah. So is that the case most of the time? Unbound can be done by 1D array. Is that the case?
Uh, so with optimization problems, it's a little more complicated because optimal substructure is the property that we need to check for. And sometimes what happens is when we define f of t like this, I mean f of whatever the if we have only a single parameter in our uh, function that we are trying to optimize, we see that optimal substructure might be missing. And so to preserve it, we might have to add a second parameter. Then we find that it's satisfied, and so having a second parameter in the recurrence uh, function leads you to a two-dimensional array, because the first parameter, whatever range of values the first parameter can take, that's the number of rows. Whatever values the second parameter can take, those would be the columns. So here there's only one parameter, so it's one-dimensional.
Thank you.
Okay, I think this poll has come up too soon, but yeah, Subbu.
Hey Omkar, hey, I want to understand, is there a same coin change problem or it's something,
Sorry,
because
is
I'm
there a
trying
what?
to, is there a we did right in the dynamic series, series that coin change problem, is it same problem or is it different? Because I'm trying to compare with the for a traditional coin change problem and this one, I'm seeing the same,
So yeah,
right?
I think coin change one, or so I had a coin change. I think coin change one was in the dynamic programming foundations,
Yes,
where
yeah,
you want to minimize the number of coins that make up a certain amount. So that was also, I mean, we are not looking at optimization problems so far, but the recurrence for that was actually very similar to the recurrence here. Instead of taking the sum from all your subordinates, you take the min uh, from all your subordinates, right? Whichever subordinate has the least number of coins that makes up that amount, you just add one more, your own coin to that. And so it was, the structure was very similar to what we have here. Instead of sigma, we would have min, and we would
Right.
also have
Yeah.
a plus. We would have a +1 here too, because the you as a lazy manager will add one more coin. Any other questions?
Yeah. Seems like familiar, so that's why I asked.
Yeah. So lead code's coin change is essentially coin change. The coin change problem I had in the foundations. It's an optimization problem. Here we are not looking at optimization. We are looking at counting, and I'm taking combination sum 4, and I'm interpreting it as because they don't have a direct problem like that on lead code. I'm just interpreting it as a coin change problem, but a permutations version,
Right.
so that we can compare and contrast it with what happens when rearrangements are not to be counted as separate solutions.
Got it.
Okay. Salish?
Yes, Omkar, thanks for the session. Um, um, so I'm trying to understand, like, for the same problem I've seen in the code where you have to find a unique combination of the numbers, the exact same problem, but you have to store the combination and it has to return all the combinations, not the permutations. I'm thinking about, how do I keep track of all those combinations as I go through the dynamic approach? So what your recommendation is for that particular problem?
Oh, you mean an enumeration version of this?
Yeah, find out, like, there's a target value and you can pick any number of times of the given choices, but you have to return a unique combination of the choices, and you have to return all the combination that adds up to that target.
Yeah, so I think when we look at the next problem, you will see that it's kind of similar. The approach that we would use for that is going to be similar.
Okay. Yeah,
I think at least in my recursion class, I remember, I think, are you talking about combination sum 2 or something like that on lead code? I think which
it's called
seems to match
combination
what.
sum.
Yeah,
I think
so I think if you look at combination sum 2 on lead code, maybe it's what you have to enumerate all subsets which add up to that target,
right.
And you can't you have to literally treat them as subsets. You cannot rearrange the numbers and
Realize it, right?
spit it as a different subset.
Right.
So I don't want to give away the key step there, because we are going to hit that key step even in the second problem, and that's when I'll try to remind you of what was the key step there to take care of. Right. So let's come back to this if your question isn't fully answered. Kyle?
Okay. So quick question. So in like the minimum coin change, we have the coin for loop on the outside. Is that because in minimum coin change, we're only using one coin as opposed to this problem, which we're able to use it multiple?
Minimum coin change also, so there also we had multiple denominations, right? Otherwise, why would it be a hard problem if there was only one coin denomination?
I guess that makes sense. Yeah. So then how come in that one we use the coin loop on the outside?
I don't remember what the code for that looked like, but I think the code would look almost, it would have the same structure as this, where you have an outer loop where the amount varies from 1 to a or whatever it is, and then an inner loop which would have which would go through all the coins. I think it should be the same.
Okay. So, okay. I guess I could just try it on an ID and then see what the values are. So it should be the same if we switch to loops as well, right? Because we're running it the same amount of times, I guess.
if we switch the loops, so the thing is, like, what would it mean in terms of so the loop ultimately is just a translation of this picture, right? So I I frankly have a hard time evaluating questions like that, because like I don't think in terms of code, I think in terms of what was the strategy, and the code just happens to be a formal way to write it up. So if you change that to some other thing, I would have to think about what does it mean in terms of the problem solving strategy if you were to change the.
I see what you're saying. So yeah, so I mean, in English, I guess you would just say, okay, we would automatically loop through the nomin. I mean, not the through the target first, and then we would be using the coins, right?
Mhm.
Okay.
Yeah, but I mean, I think you should think about it in terms of what we did here. If
Mm.
that can be mapped to this kind of a picture, maybe with a slightly different interpretation, then it would be fine. Otherwise, I'm a little skeptical of. I would remain a little skeptical of making those kinds of changes.
Okay. Thanks.
Okay, so
Right. Okay.
yeah,
A quick question. So I think for this solution, was that the solution that you showed? Was it runnable? This one.
this one, yeah. So
Okay.
I think
The reason is I ran the same code. The interesting part is like let's say for 1 to 5 input, the answer comes 9 in the same code, which is supposed, and the correct answer is 4. And switching the for loop, it works fine. So the way is like you put the for loops first as a coin, then the amount, then it works fine. I'm not sure why.
okay. So you're basically saying what Kyle just asked. Uh, well,
Yes.
I tested this code. This code ran. If you look here, the structure is basically the same as what I wrote, the pseudocode
Okay.
for coin in nums. And it ran for me. I mean, yeah, I don't know if there's any other.
Okay.
Um, okay, so you're saying if you change the order, it would still run.
Yeah, if the order is first coin of for loop and second one is amount, then it will work fine. Because I ran for the input 1 to 5 as a coin, and the target is
I see.
5, then the answer will be wrong.
Well, but this should run. I mean, we can evaluate whether that would also work correctly. But
Sure.
this code, it does run correctly, so I don't think you should get an error if you
Sure.
translated this pseudocode into. Make sure that the base cases are
Yeah.
handled correctly. So if you are iterating over coins and then um,
It's hard to imagine. I mean,
coming up with the target, I'm not. Yeah, it's hard to say what that even means, right? Because
yeah.
when you take a sequence like 1 to 1, right? 1 cent followed by 2 cent followed by 1 cent. How exactly is this going to get mapped to that? Um, because I can see here that if we start from the overall amount, we subtract 1, then we subtract 2, then we subtract 1. But if you are iterating over coins and then the amount, um, yeah, I mean, there must be some other way to interpret it, which is why it's running correctly. But at least because since my train of thought was what I described over the last half an hour, I'm unable to shift it from this to, like, I need a different starting point rather than looking at the end point and then trying to reconstruct a different starting point.
Yeah, that's correct.
Yeah, but something to think over. If it's running correctly, then